This is the state of this Saba Freiburg W2 since the last time. After the initial inspection, I went and had a look at the primary circuit of the power supply, and I believe it is now ready to do the first power up. Let's just have a quick look at the schematic and I'll show you what's been tested so far. So what I've done so far is starting from the AC input, these 2 points over here. This is the mains. We have the mains coming in through the switching circuit, which has been tested. It's working fine. We had these two safety caps here. They weren't safety caps, they were just two 5 nanofarad capacitors. This is for cleaning up the RF that may be bled back into the main circuit. So that was replaced. These guys tend to fail spectacularly by creating a short to one of the from one of the mains lines, either the live or neutral, to the chassis. That part there is earthed. These are replaced with safety caps. They were hidden behind the transformer just as the original one was. I joined 2 safety caps, put it in some black heat shrink and soldered it back into place. The mains then comes into the 220 volt tap on the primary of the power transformer. There's a 1 amp fuse which is working. It was tested. The secondary line over here has a 180 milliamp fuse, which is also okay, before it goes to the one of the AC inputs of the selenium rectifier. The other line goes to the other AC input of the selenium rectifier. Now all these tests were done for continuity, nothing else. No power up has been done as yet. The negative output of the selenium rectifier goes to the negatives of those two 50 microfarad capacitors, which are in the can that I showed earlier. The capacitors themselves have not been checked, hence the unpainted symbol here. The continuity of the choke has been checked, and that point there, the negative of those capacitors, as I said in the previous video, is isolated from ground. It is not shorted to ground. So ground, between there and ground we have this 20 ohm resistor which measures 20.7 ohms, so it's well within spec, very well within spec in fact. The positive supply, the B plus, coming out of the selenium rectifier then goes off to this connector, which is the speaker connector on top of the chassis. The speaker is actually connected with a plug. This is kind of weird. If that thing happens to go in the wrong way, we'll end up with 200 and many odd volts on the speaker connection. So you have to be very, very careful when you plug in the speaker. You normally would plug it in with the unit disconnected anyway. And these sockets only go in one way, so you should not try and force them because you may get them the wrong way around with some pretty dramatic results. So what we have now is this circuit has been checked. There are no shorts going off from there. That's been checked with the continuity as well. I see no obvious reasons for this thing to not power up, but what we're going to do now is power it up with the light limiter, which I've set up here and will show you in a second. The way this light limiter works is as follows. I have mains coming in over here into the light limiter. It then goes through a metering output. These two connectors here go to an ammeter over here. That can be bypassed if I don't want to check the current. I can then leave it active or bypass. I'm leaving it as active. At the moment it is off, and I can switch in as many lamps of these lamps as I want. I have a 40 watt lamp, 60 watts and 60 watts. So the thing to do is to try it on and bring in the lamps slowly. Put in first 40 watts and see if there's any shorts. This will measure the actual voltage coming out of the socket here through into the radio. If there's some dramatic short in there, what we'll get is the light will go on very, very bright. The voltage will be very, very low. 40 watts does not allow too much current to go through, and therefore we have quite a good safety margin in case there is some dramatic shorting that goes on here. We can also monitor the current that goes in as we switch it on. And that's what we'll do next. So we'll watch that and see how it goes. Let me switch this on. It is now switched on, plugged in, switched on, and we have no voltage here because the lamps are off. All the lamps are inactive. I am going to activate one of the lamps, that 40 watt lamp. We still have no current because the radio is currently switched off. So I'll put the volume low and let's power it up and see what we get. The light went on very brightly. Now it's dimming slightly. The voltage there is indicating about 180 volts. So I have these dial lamps have come on. We have the meters on 1 amp. On 1 amp range, we have about 150 milliamps being drawn. So far so good. I'm going to switch on the other lamp. We still have, let's see if we have any noise. Still have no noise. I have no antenna here. I just want to listen for static. Let's switch on another lamp. What we've done here is made the resistance made the resistance lower by putting 80 watts in series with the radio. The voltage has come up slightly to about 180 volts. The current has also gone up to 220, 250 milliamps. And what do we have? We're getting a hiss and we're getting some hum. Oh, that's great so far. Right, let me give it another one. So the voltage has now come up to 190 volts. The current is at about 280 milliamps. So far so good, and we do have a loud hiss. I think at this stage I can try the last one, and I have the voltage up to 200 volts. I think at this stage I can actually push the bypass. Let's feel if the transformer is getting warm or anything like that. Transformer is not warm. I can see the glow coming from the tubes, so the 6.3 volt supply is active, at least on some of the tubes that I can see. I have no shorts, I have no drama. So I'm going to hit bypass. Right, what this has done is it's applied the full AC voltage to the radio without the protection of the lamps. And we've got 230 some odd volts on there. I have a 235, usually about 235 volt reading from my house main supply. And as far as current's concerned, I am at 380 milliamps. And I have the hum on FM. So I'm going to connect a short antenna to there and see if we can pick up anything. We've got the sound, which is promising. A bit noisy and scratchy, but that's to be expected. Let's see what we get with the antenna. Right, with a very short antenna, literally this over here, connected to the FM, to one of the dipole inputs. Let's see what we got. Beautiful. Very noisy, but it's there. So we have FM, that's great. So I've connected an external antenna to the antenna terminal, and we're going to see what we get on the other bands, long wave, medium wave and short wave. Let's try long wave first. Static. It seems to be receiving as much as it can over here on long wave. I don't receive many transmissions anyway on long wave. Try medium wave. We have music. So we are receiving on medium wave. Let's try short wave. This button's stuck. Medium wave button gets stuck. Got to remember that. Well, nothing on shortwave. Okay. What we're noticing here is a very loud hum, even with the volume way down. I'm not sure that you can hear it, but it's definitely there. Lots of hum. You can probably just hear it now. And that seems to indicate that our two filter capacitors are probably not as effective as they should be. So that's what I'll be doing next. I want to change this thing to the 240 volt input. I'll test some voltages before I do that, but I think I'll be putting it into the 240 volt input, then testing the voltages to see whether the selenium rectifier needs to be replaced. If it does, I'll need to put a resistor in series before the first filter cap to bring the voltage down somewhat, because the selenium rectifier tends to have a significant voltage drop, and I don't want to risk the voltage coming in being too high. The schematic shows 230 volt AC out, in other words from the transformer, so into the selenium rectifier should have 230 volts. The output of the selenium rectifier, the first filter cap, across the first filter cap, I should have a 270 volts. So that's what I'll be checking next and reporting back. And let's see what we have coming into the selenium rectifier. In other words, the output of the transformer. 238 volts, so it's 8 volts over what it's supposed to be. That's our AC input to the selenium rectifier. Another important number to check is the voltage going to the heaters. In other words, the heater line coming from the transformer, which should be about 6.3 volts. Let's see what we have. 6.97, 7 volts. It's a little bit high. We want that down to 6.3. Now on DC, what have we got coming out of the selenium rectifier? We want 270. Let's see what we're getting. We've got 249 volts. 249 volts versus 270 desired. That's a little low. So what we have is too much voltage coming into the selenium rectifier and too little coming out. And the heater supply is about 10% too high at 7 volts. So we'll need to do something about that. Another thing I want to check is, if you recall, the capacitor, the two filter capacitors are not referenced to ground, and there should be a voltage between ground and the negative supply or negative point of the two filter caps. Let's measure that. So connected to the chassis over here, and I have access to the ground of the caps. I've got minus, get a good connection, about minus 3.13 volt, 3.1. It's alternating somewhat. 3.1 volts, okay, about 3.1 volts. That is across that 20 ohm resistor. That figure is important because it'll tell us how much current is actually flowing through, or flowing out of the selenium rectifier as well, so we'll know what kind of resistor to put in. Let me just get that a bit more accurately. 3.2 volts, call it 3.2 volts, negative. Fair enough. Another thing I want to check is how much ripple, AC ripple, have I got on the B plus line. That'll give us an indication of the state of the first filter cap. So I'll put it back on AC volts and go and measure across the output of the selenium rectifier. 9 volts AC RMS, 9.1 volts of ripple. That's pretty high. So that cap is not doing its job properly. We already gauged that from the hum we're getting out of this thing. And the reason we're getting hum without any volume is because in the push-pull configuration that we have on this amplifier, the output stage, we have a B plus going to the center tap of the output transformer. So what we're getting is, because we're getting no signal on the other 2 points, in other words, the signal driving the output transformer, we've literally got 100 hertz of hum constantly across the speaker. They should have an effect of cancelling each other out somewhat if they're going through with the signal, but in this case it is pure hum even without a signal coming into the output transformer. So next stage, capacitors, swap these out. I think I'll be stuffing them, stuffing the filter caps, and do something about the voltage supply and the voltage readings. I put a probe across the selenium rectifier output, and what I want to see on the scope is I want to see what the ripple is exactly on here. At the moment I've got this thing DC coupled, 100 volts per division, as expected, 200 and something volts over there. If I AC couple it, reference to 0 again, and let's start putting this up. There we go. There's our ripple. What we've got here is a 10 volt per division. So what we're actually reading over here is we're getting -16 volts peak, minus 16 volts, so 32 volts peak to peak, 32 volts of ripple peak to peak. And as far as the frequency is concerned, 100 hertz as expected. So what we've got is 50 Hertz coming in, getting rectified by the selenium rectifier, full wave rectification. So we expect the ripple to be 100 Hertz, and that's exactly what it is. So that's what we have to reduce dramatically.